Today we're going to talk about COVID-19 fatality rates for the southern region of the United States. There are 17 states in the southern region of the United States. This analysis is preliminary and exploratory. A logistic regression is performed using a binary response of COVID-19 death rates, often called fatality rates, over 5%. Now this is in a county with a death rate over 5% will be given a 1, otherwise 0. We're going to look at the Johns Hopkins deaths versus cases by county. The binary response in the regression will be 6 independent demographic variables. There's a disclaimer here. The views, results, and information presented here are solely those of the author and do not purport to reflect the views, results, or information of any institution or entity associated with the author. At the time of this presentation, the model has not been verified using a holdout sample. Normally, I would create 2 data sets, a training and a holdout sample. The holdout sample would be used to verify the model. The agenda today is going to start with caveats. I'm going to show you my source data. I'm going to talk a little bit why I chose not to use a random forest and why the 5% cutoff rate for fatality rate. I'm going to go through some findings. I'm going to talk about the model independent variables. I'm going to talk about the independent variable contributions to the highest risk. We're going to do some model prediction versus observed probabilities. We're going to look at concordance and the ROC curve. I'm going to describe the independent variables, and I'm going to do in-depth chi-square and index analysis, basically odds analysis of the character variables. Now I use a technique which I call Optimum recursive binning, which is used to bucket the independent variables. I do this for both the character and the numeric variables. I'm using a list of 327 potential independent variables. There are actually many more, but these are somewhat normalized so that I can use them in the analysis. I'm going to show variables. I'm going to sort and show you the variables with the highest chi-squares. I'm going to show you examples of collinearity, which is common when you have 327 variables. I'm going to run the automatic proc GLM select to show you what SAS would select as the best model. I'm going to show you my final model. I'm going to check my final model for collinearity. I'm going to show you a ROC curve, concordance, and finally a gains table. And then I'm going to show you the detailed chi-square analysis of all 327 variables. There's some caveats with this. This is purely exploratory, not inferential, and it was done mainly to demonstrate some algorithms and reports that you may find useful for predictive analytics. I'm not a medical writer or skilled clinician, so the results should be taken with skepticism. The independent variables were linearized using optimal recursive binning. This is a program developed by myself and Clemens van Bonscha of the Netherlands. I didn't use dummification because the target sample for the southern counties there were only 109 counties in the southern region of the United States, 109 out of 1,422 counties that had a fatality rate over 5%. Bucketing was restricted to 2 or fewer levels. Variable coefficients were restricted to positive values. This makes the interpretation much easier. Okay, the input data consists of the 2015 hospital cost report data, which is public and on the web. All this data is on the web. 2018 skilled nursing facility cost reports, 2018 American Community Survey census data, and census SF1 data, October 10th, 2020 Johns Hopkins COVID-19 data, which is a day-by-day compilation of deaths and cases due to COVID-19. I decided not to use a random forest. Random forest tends to be more of a black box method. With some clinical experience and recent literature, I felt a logistic regression could provide epidemiological insight. Why a 5% cutoff? 3 to 5% fatality rates are quoted in the literature for the average U.S. death rate. So I felt exceeding that was beyond what would be typical. Model independent variables. Okay, there's the states. I split the states into 3 buckets. Population of the county, crowding in the county, percent of population over 85 years old, percent of population on food stamps, non-family households. I analyzed over 300 independent variables. Here's a description of the independent variables. The states with the lowest risk, those with less than 2% death rate, were placed in one bucket, and those greater than 12% were put in the highest bucket. There's actually 3 buckets. Population, it seemed like 10,000. The risk was much lower, much higher for counties with less than 10,000 population. The lowest risk was counties with greater than 36,000 population. Otherwise, more rural or more or less dense counties had a higher risk of COVID-19. Persons per room. This is kind of an interesting one that I did some investigation on and felt that it could be quite useful. It splits on 1.5 persons per room. In other words, if you have more than 1.5 persons per room, it's considered a crowding condition. And this is often done because for economic reasons. Percent over 85 years old, again, less than 2% or greater than 2%. Percent on food stamps, less than 20% had a lower risk than greater than 20%, kind of maybe a surrogate for poverty. And living alone, which is basically non-family in households. Lower risk if you had fewer percent living alone. Higher risk for those with higher percents of living alone. The logistic model has potential for risks, and this is the overall major finding, that you can use this model to identify or assess counties with higher risk factors. In fact, you should be able to use this to maybe estimate future fatality rates as more John Hopkins data comes in. The final model independent variable risk assessments. These counties, Georgia, Maryland, Missouri, Texas, Virginia, and West Virginia, are almost twice as likely to have a death rate over 5%. Again, we saw populations under 11,000 were twice as likely. Counties with high level of crowding are twice as likely. Counties with 2% of the population over 85 are 40% more likely to have a death rate over 5%. Counties with food stamps at over 80% more likely to have death rate over 5%. Non-family households, which are really percent living alone, are almost twice as likely. West Virginia had the highest number of counties, percent over 5%. Micro has twice the probability. High African American counties are almost twice as likely. Counties with 1 or fewer hospitals. This is kind of interesting. In fact, there's quite a few. I should bring in the claims provider data because it looks like I only had a few variables that measure health care. I have insurance rates, I have uninsured rates, I have hospitals, I don't have, I think yeah, I did have number of providers, but I think this might be an area to look at in more detail. I don't know why we got it 10 times here. I have to do more work on that. Counties with more than 17% disabled are twice. Counties with percent poor over 17% are twice as likely. Less than 40 beds, and it's 3 times as likely. Here's another this coming in. We have this healthcare component, which needs more analysis. You know, poor counties are twice as likely. Counties with less than 25% college graduates are 4 times as likely. Counties with 37% or more 65 years or older are almost 3 times. Counties with median home value less than 100,000 are twice as likely. Again, a surrogate for probably poverty. Now here's the 327 variables, independent variables that I used in the model. There are actually many, many more variables, but you'll notice that a lot of these are percentages. It's difficult to sometimes work with actual counts. You can compare the percent from one county to another. Comparing the counts can be dependent on a number of not only population but other counts. So I decided to hone in on percents for the most part. One of the things I like to run kind of right away when I have my 327 variables linearized and put into buckets, and if you notice there's an underscore in front of these variables, that just means the variable has been put into buckets and linearized. We'll talk a little about that later. So here's what SAS came up using the general linear model selection procedure. It actually comes up with a higher R-squared than my model, but I seldom find the model, this kitchen sink approach, to give the model that I would finally agree on. I try to use my knowledge and the literature to select the variables. Selecting the variables is a very time-consuming proposition. So how does our model fit? Here's a comparison of the predicted and observed probabilities of a county having a death rate over 5%. Now the way this is done is you rank the scores from the model and you put them into deciles. So you're putting your predicted values, your scores, into deciles from a highest percentage deciles to the lowest percentage decile. And then in each of those deciles, you also have the actual percent, the actual probability of a county having a death rate over 5%. So you can see the model predicted on average about 30% of the counties would have a death rate over 5% if they were in a high decile. And 27 actually observed. Drops off fairly quickly, and of course at the last decile you're just about at 0, and we'll see more about why that happens. But and also you'll notice that the prediction is quite smooth, and the actual can become quite lumpy because we only have up to 3 buckets, and a lot of them are just 2 buckets, and it discretizes the data, so certain combinations can cause lumps to occur in this falling curve. This is just the number of counties there are only 109 counties that had a death rate over 5% of the 109. So 38 out of the 109, because there's only 109 counties that had a death rate over 5%. 38 of those 109 were in the first decile. falls off 26, 15, and then of course we get down to 0. So this is just the counts in the deciles of the counties with death rates over 5%. I like to look at the highest scores, the highest average scores, and look at the contribution by the different independent variables to the high scores. Population is the strongest independent variable in terms of contribution to the highest scores. The lowest is state, and you can see the next highest is percent living alone, which is non-family households. Food stamps, I think, is next. Persons per room. So this gives you an idea of the weight of the different independent variables. Now, percent concordant. This is an important measure of how well your model's doing. And the best way to explain this is to create two data sets. One with DR death rates over 5% and one without death rates over 5%. In other words, death rates less than 5%. You compare all pairs of counties in the two data sets. The percent concordant is the percentage of pairs where the county in the greater than 5% death rate data set has a higher probability than the observation in the DR non-event data set. You hope your non-events have a lower probability of having a death rate over 5%. So if the percent of pairs with the county has a higher probability than the observation in the 0 data set. Now these are predictions, not actual values. So you call that concordance. And that's how you get the 75.4. Another measure, which is measuring something very similar. In fact, this is what's called the receiver operating characteristic curve. I think that's what it's called. Now it measures how discriminatory your model is. You look at the x-axis and it tells you about incorrectly identified counties. I mean, the model didn't correctly identify them out, and this one is where the county is correctly identified as having a death rate over 5%. What you really want to see is you want to see a 0 here, and you want to see it go to 1, go right up here to 1, and not have any of these false positives. Now the area under this curve should be the same as the concordance, about 70.75 or 75%. The higher this curve is toward the value of 1 here, the higher it goes, the better, the more discriminatory your model is. Okay, let's talk about how I got these independent variables and what they look like in detail. This is called chi-square. I call this chi-square analysis. And again, we're looking at those 17 states. We know that 109 of the 1,422 counties, or 7.6% of the 109 counties, have a death rate over 5%. That 7.67 is going to be a very important number. It's going to appear in the denominator of quite a few analyses. You know, how much higher you are than that overall average can be thought of as the odds that that county is going to have a death rate over 5%. Let's start by looking at, first of all, the chi-square 50.55 is just astronomically significant. So these states can be used to classify risk quite effectively. From lowest risk to highest risk. Lowest risk is 1, highest risk is 3. Now if we look at the high risk area, we got Georgia, Maryland, Missouri, Texas, Virginia, and West Virginia. Georgia had 19 counties with a death rate over 5% out of 159 counties, or about 12%. West Virginia had the highest. It had 8 counties out of 55 with a death rate over 5% or 14.5%. Now the total number of counties in this high area is 88. There are 619 healthy counties for a total of 707 counties in this high risk group. That's 49% of the 1422 counties available overall. The percent of the counties, the average percent of the counties with a death rate over 5% is 12.45%. We know the overall average is 7.67. So if we divide 12.45 by 7.67, we get the odds 62% more likely that you're going to be in a county with a death rate over 5% if you're in these group of states. The Deep South, there's 7 states in the Deep South. In the Deep South, you're 44% more likely to have a death rate over 5%. Micro, you're 30% more likely if you're in a micropolitan area than a metropolitan area. Population, this is the single strongest variable in the whole analysis, and it's a good variable from the census. If your population is less than about 10,000 or 11,000, then you are 2.25 or more than twice as likely to be in a county with a death rate over 5%. And if you're over 36,000, it's extremely low. You only have a point. It's very low. Percent living alone is again quite strong. Persons per room is the second strongest, I think. We're twice as likely to have a death rate greater than 5% if you're in a crowded situation. Food stamps, you're 80% more likely. If you're over 85, if you have over 2%, if over 2% of your population is over 85 years old, then you're 40% more likely. Now this gives you the chi-square, the descending chi-squares for all 327 variables. Now death rate less than 5% is perfectly correlated or related to our dependent variable, so you get an astronomical chi-square. And it does a perfect split. If you look at the detailed chi-square analysis, you'll see a perfect split on DR, as you expect. Average county mortality is also extremely strong related, because that's another measure. It's deaths over cases. Disabled came in next. Group quarters came in. Average household size. There's population up there toward the top. There's 3 measures of population, and they're just about the same in this data. One of the things you need to do, I like to do, is look at collinearity among your independent variables. If you look at percent born in a different state or percent born in the current state, you know those are very strongly related. It's probably not, in this case, it's some little rounding and things going on, so it's not perfect, but with this kind of inflation, it's really percent born in different state is 1 minus percent born in current state. These are all kind of yes, no related sort of things, military or civilian. Down here, when you see a question mark, that's when it's an absolute perfect relationship in the data. The numbers are 1 minus, in this case, no computer and computer, pretty much 1 minus the other. So these are all very problematic. variables. There's a lot more of them. I just wanted to give you an example. You should do this. Anything over 2.5 is of concern. Now, one thing I do that I don't know if other people do this, is nowadays computers are so fast and so powerful that I tend to look at all possible models. It actually doesn't look at all of them. It makes a decision when the R square is dropping to a certain amount that it will not continue to look at combinations. But I tend to look at the top 1,500 of all possible 6 variable models. This is the one. This is not the one I chose, but this is actually quite close. This is a set of 6 independent variables. Each of the coefficients has a pretty good weight. And you can kind of compare these weights, because the way I do linearization is it tends to be low between like 0 and 2. So the coefficients I like to see, between 0 and 1, and I like to see them sort of above 0.5. So and I like to see them all positive. So here's the top 6 variable models from the all possible models. And I go through these. This takes me quite a bit of time, because I look through at least the first 100 of these in detail to see how the variables are mixing together, which ones are, have been noted in the literature, those kinds of things when I pick the model. You have to check your final model for variance inflation. You do not want to see anything over 2.5. And we don't here, and we see these are the variables I selected in the final model. The estimates are all over 0.5. They're all significant, and the variance inflation is all less than 2.5. The gains table is a source of information for graphing and for understanding the power of your model. We saw in some of the graphs, we saw the predictions versus observed values. Now, the gains model gives you all the counts you would ever need. So you can plot lots of relationships from this. So we start out, again, keep in the back of your mind that the overall fatality rate, county fatality rate, is about 7.67%. 7.67% of the counties had a death rate over 5%. And let's look at some of these columns. So we group it in deciles based on the scores, this is what we did with the observed versus predicted model. So we see healthy counties without a D, or healthy counties. Here's the number of healthy counties. For instance, in the first decile is 103. There were 38 that had a death rate over 5%. The total in the decile is 141. The percent of the counties with a death rate over 5% was 26.95%, or 27%. That's the 38 over the 141. I'm sorry, the 38 over the 109. Okay, that should be 109. 38 over the 109. No, that's, oh shit. What am I doing here? Let's see. Should be the 38 over Oh, 30, that's right. I'm sorry. It is the 38 over the 141. That's the percent in the decile. We have 38. We have a total of 141. 38 over 141 is 27%. The cumulative number of of counties with a death rate over 5% is 109. You got 38 of them in the first decile. Counties with death rate greater than 5% as a percent of all counties, here we're looking at not the 38 over the 141, we're looking at the 38 over the 109, which is the percent of all counties with a death rate over, so we have 34% of the counties with a death rate over 5% in the first decile. This is just the cumulative counties, and cumulative, this is just the cumulative count all in each decile. You're just accumulating this first column, and there's your 1422, which is all the counties in the 17 states. You have 1313 that don't have a death rate over 5%. Here's your 7.67%. There's the 2695. And over here we have sort of the odds of a decile will exceed the overall average. This is an important number. The 3.52 means that the counties in the highest decile are 3.5 times more likely to have a fatality rate over 5%. Those counties tend to be high in all of the independent variables. So that's one of the more important numbers. Again, I repeat some of the values here, but what's of interest here is these max score, mean score, and min score. So in the highest decile, if you're high on every single variable, I believe this is the case, you have a 51% of those counties will have a death rate over 5%. So the odds are like 50% you're going to be in a county with a death rate over 5% if you're high in all of the categories. Here's the mean, which we saw before, is about 30%. The minimum is 21% in the highest decile. Of course, it goes down to just about 0 here. We actually plotted some of this. We plotted this one prior to this. Here I've been all 327. This is where I spend probably 50% of my time. I go through all of these variables, all 327, and I look at the chi-square splits, because sometimes you can have very low coverage. You have a small amount, and you really don't want to use that variable if the split wasn't reasonable coverage in both buckets. So you have to look at a lot of things to pick out the variable you want, not only the chi-square being very high. Here's the perfect split, because I'm splitting the dependent variable, and of course it accurately split exactly 13, 13, and 109 in the 109 counties with a death rate over 5% and healthy counties. So this does a perfect split. And population is the next strongest. These are in order of power. Total pop. See, these are the same, measuring the same thing. Total pop, top SF1. They're just estimates of the population. And that's about it. Thanks for listening.